So let's start with a very simple system of equations. In this case, I'm not putting numbers. I'm just using algebraic notations, 3 by 3 system of equations. Okay. Now suppose we use Gauss-Seidel for solving this system of equations. All right. So therefore, we are going to do iterations, and I've introduced an iteration index k. So in the very first equation, you see what we are doing here is that I'm solving for phi1 in terms of the other two guys. So I've transposed them over to the right hand side, and of course they have indices k, and of course phi1 has an index k plus 1. Okay. Similarly, after I've done that, then I move over to the second equation. This is kind of like scanning through your nodes that you're doing in your homework. Remember, every equation comes from one nodal equation. Okay, one equation per node. All right. So second equation, by the time I go there, I do the same thing. However, when I solve the second equation, the first equation value is already known, and therefore that has an index k plus 1 instead of k. Okay, and by the time I get to the third equation, both my phi1 and phi2 are known. I've already solved for them, so they get indices k plus 1. So this whole process now completes one sweep through the computational domain. Okay, imagine you have 3 nodes, so you've solved 3 equations. All right, this is one sweep of the Gauss-Seidel iteration. Now I can rewrite those equations such that I have the k plus 1s on one side and the k minus, or the k's on the other side. Okay, so I'm going to pull these terms back over to the left hand side because they have indices k plus 1 and so on. So this is what I end up getting. Okay, any questions so far? If I write it in matrix form now, okay, and it's so much easier for me to use this smartboard when I don't have WebEx turned on. Okay, so when I write this in matrix form, now what I've done here is I've divided each equation through by their diagonal coefficients. So first one has been divided by a11, second one has been divided by a22, third one has been divided by a33. So I'm using these barred quantities, okay, where each equation has been divided by its diagonal. Same thing for the right hand side, the q has been divided by the diagonal too. And so this is the matrix form of this equation. Okay. So on the left hand side I have the k plus 1s, on the right hand side I have the k's. Okay, and of course you still have your source term. All right. So you see here that this matrix, this is a lower triangular matrix. This here is an upper triangular matrix. Okay. So we can define a lower and upper triangular matrix, and the custom is to define it with a negative sign. Okay. But you know, you can do the derivation with a positive sign too, but that's how people usually do it, with a negative sign. And when you do that, then that equation that I showed you, the last equation on the previous page, is basically written in matrix form like that. I minus L times phi k plus 1 is q bar plus u times phi k. Okay. Everybody with me so far? All right. And so now in matrix notations I can say, okay, my phi k plus 1 is I minus L inverse times u times phi k. So I'm doing basically taking this, multiplying with the inverse of that on both sides of the equation. Okay, and I get that. And this matrix here, I minus L inverse times u, is denoted by B. Okay. That B is called the iteration matrix. Okay, it is very specific to, in this case, the structure of that matrix, I minus L inverse times u, is specific to the Gauss-Seidel iteration. If you use another iteration scheme, it may be of a different form. Okay, but it will be some combination of the elements of the A matrix that we started off, because L obviously has coefficients of the A matrix, U also has coefficients of the A matrix. So it's in some manner related to the coefficients of the A matrix, but it's not the A matrix itself. Okay? So this is called the iteration matrix. Why? Because think of this as a matrix operation. We are operating this matrix on the phi vector of the previous iteration to get the phi vector of the new iteration. Okay? Any questions so far? Now, convergence is defined as the state where the results at two successive iterations are identical. Okay? Now, this is sort of an alternative definition of convergence. We don't monitor convergence by this criterion because as I said before, one of the problems with doing that is maybe there's a bug in your program and phi k comes out to be phi k plus 1 because of that. So it's kind of dangerous to use this. However, when your L2 norm goes to 0, this is exactly what happens. You get the exact numerical solution, which I am denoting by phi e, and that is also equal to the solution at two successive iterations, okay, because the residuals have dropped to 0. So the phi is not changing anymore. Okay? So therefore, this equation that I had earlier, this one here, okay, I can replace the phi k by phi e, exact solution, and also the phi k plus 1 by phi e, the exact solution. Okay? And that's what I have here. So that same equation must be also satisfied by the exact solution. Okay? If I subtract one from the other, equation number 1 being this equation here, okay, the iteration equation, and iteration number 2 being the iteration equation written with the exact solution. Okay? If I subtract one from the other, then I get that. Phi exact minus phi k plus 1 is b times phi exact minus phi k. Okay? This, if you recall, we talked about this in the previous class. This is known as the convergence error. It is the error between the exact numerical solution and the solution at any given iteration, okay, due to partial convergence. So that's what we refer to as the convergence error. And so if we denote that by epsilon, then we can say epsilon at k plus 1. So this is the convergence error at the k plus 1th iteration, is this B matrix times the convergence error at the kth iteration. Okay? So that is why the B matrix, an alternative name for it, is also the amplification matrix. Okay, so it's called the iteration matrix. It's also called the amplification matrix. Why? Because this is kind of like an amplifier if you think about it. Okay, I take the error at a certain iteration, I multiply it by B, that gives me the error at the new iteration. So this is like an amplifier. Okay, it may actually damp out that error or it may blow it up next iteration depending on what B is. Okay. So that's why it's known as the amplification matrix. Now, of course, as I just said this, that whether the error actually grows or decays with iterations will obviously depend on certain characteristics of the B matrix. Okay. Now think of it as a scalar. Suppose epsilon is a scalar. Okay. So I have epsilon at iteration 5. Okay. And from that, I'm calculating epsilon at iteration 6 is equal to some scalar b times epsilon at iteration 5. Now, it's pretty obvious that b has to be less than 1 for the error to die. Okay? Otherwise, when you keep doing it, if you do n iterations, it will become epsilon at n is equal to b to the power n times epsilon at 1. Right? And if b is greater than 1, then some number greater than 1 to the power n, if n is a large number, is a huge number. I mean, 1.2 to the power 100 is probably a few million. Okay? So it will quickly grow and just blow up. All right? So it's easy to think of it in terms of a scalar because then we see, okay, b must be less than 1. Otherwise, the error is not going to die out. Okay? If it is less than 1, even if it's 0.99, then with successive iterations, it's becoming 99% of each iteration value. Okay. Now, in the case of a vector, which is what we have here, all right, the criterion is that the eigenvalues of B must be less than 1. Okay. So for a scalar, it's just one number. For a vector, it's the eigenvalues of B, and that's denoted by lambda with B within brackets. Okay. And notice the absolute value sign on the two sides. That means that we don't care whether the eigenvalue is positive or negative. What matters is its magnitude. Is it greater than 1 or less than 1? Okay. Now, it also says that all of the eigenvalues must be less than 1, which automatically means that the largest eigenvalue must be less than 1. So we don't really care about all the eigenvalues. All we care is the largest eigenvalue less than 1 or not? Okay. Now, how do we find the eigenvalues? We talked about this maybe 3 or 4 classes ago when we talked about the Stone's method. Before that, I did sort of a review of matrix algebra. That's when we talked about this preconditioning and all that. And we said the way to find that is you find the determinant of B minus I lambda equal to 0. Okay? And I showed you some examples where we were trying to calculate the eigenvalues of the A matrix. Okay? And so this will result in a polynomial equation, essentially. Okay? N-dimensional polynomial equation with n roots. Some of those roots will even be complex. Okay? So this is pretty tough to do. I mean, if you think about calculating eigenvalues of a matrix, people don't really solve polynomial equations to calculate eigenvalues of matrices. There are other methods. Okay? That's usually taught in linear algebra classes. So even though we have established a criterion for finding out whether the iteration scheme will be stable or not, it is not a very practical criterion in terms of implementation. Okay? We can't calculate the eigenvalues of B and say, okay, this will be stable. Calculating the eigenvalues of B is probably tougher than solving the equation and finding out it doesn't work. All right? So we have to have an alternative method. Now, the savior is the fact that all we need is the largest eigenvalue. We don't care about all the other eigenvalues. Okay? And this is what people kind of realized very early on and said that really all we are interested in is the largest eigenvalue, so why even bother about finding all the eigenvalues? Let's try to focus on a method where we can do that. Find the largest eigenvalue. Okay? So this largest eigenvalue is also known as the spectral radius of convergence. Okay? This is a very, very important term you will see in the numerical analysis literature all the time. People will say, oh, by preconditioning the matrix, we reduce the spectral radius of convergence. Okay? That basically means we reduce the largest eigenvalue. So the stability criterion for any iterative solver, okay, again, this is for linear equations only, remember. No, there is no theory for nonlinear equations. Okay? But if you're doing iterative solution of a set of linear equations, the stability criterion is that the spectral radius must be less than 1. Okay? And the spectral radius is nothing but the absolute value of the largest eigenvalue. The stability criterion doesn't say anything about the rate of convergence. It simply says whether a system will converge or not. Okay? It doesn't tell you that, okay, you know, if the eigenvalue is 0.8, then if some other method has 0.9, then 0.8 is better than 0.9, and therefore 0.8 will converge faster. No, it doesn't tell you that. It simply tells you that both 0.8 and 0.9 are less than 1, and both will converge. Okay? Just because one's eigenvalue is smaller than the other doesn't mean it will converge faster. And we'll get to that in a moment, why that is so. Okay? So keep that in mind, that don't just compare the spectral radius and say, oh, this is faster than that. All right? the rate of convergence of the scheme depends on the condition number of B. And this is the reason. So what happens is, even though your lambda max in the two cases, let's say one is 0.8 and the other is 0.9, but by the same token, the minimum lambda might have also changed in the two methods. Okay? So you have to look at the ratio of those two to see which one actually is smaller. Okay? So whichever one has the smaller condition number will converge faster. Okay? All right. So this is our definition of condition number, and this is just sort of side information. If you ignore the fact that the smallest eigenvalue also changes, then you can say that, okay, the rate of convergence also depends on the maximum eigenvalue. And we will find that when you compare, later on we will see that when you compare between two different methods, you can't just compare the spectral radius of convergence and say that one is better than the other. Okay? But when you're comparing the same method for two different mesh sizes, for example, then you can do that, because what happens in that case is that the smallest eigenvalue doesn't change between the two mesh sizes, but the largest one does. Okay? So that in that case, looking at the spectral radius is good enough when it's the same method. Okay? But if it's two different methods, no, you can't do that. All right? That's basically what this is saying here. So in summary, our stability criterion is that spectral radius less than 1 will give us convergence. Spectral radius greater than or equal to 1 will give us divergence. Okay? All right. And this is just sort of rule of thumb that the smaller the spectral radius, the faster the convergence, if we are looking at the same method. Okay? So for example, for two different mesh sizes. All right, so at this point, we are kind of switching gears, and as I said, so the challenge now is how do we calculate this guy? We have established a theory that this is our convergence criterion, but we need to calculate the spectral radius. Okay, so how do we do that? And that is where we start using Fourier series. Okay, so I'm going to review this a little bit and then move on. So we all know this, that a continuous function can be represented by an infinite Fourier series. Okay, the interval for this is minus infinity to plus infinity. The process of writing the function as a Fourier series is often known as Fourier or spectral decomposition. Okay, the word spectral means it's an adjective for frequency. Okay, so something that is related to frequency. Now, one of the important features of the Fourier series are that the terms are linearly independent. In other words, if I take the first term of this series and the second term of this series, I cannot linearly combine them to produce the third term. No, that's impossible. Okay, they are by definition independent of each other. Okay. Both the sine and cosine components are important to retain whenever you do a Fourier decomposition, and that's because there may be some cases where you need the sine terms and there may be other cases where you need the cosine terms. For example, if I wanted to satisfy this function f at 0 equal to 0 using this Fourier series, and I did not keep the sine terms, then it won't even work, because what will happen is you have to set cosine of 0 is 1, so which means all of the AMs must go to 0 in order to satisfy f0. And that would basically give you a trivial solution. Okay? So you can't even have a function with that if all of the AMs go away. So therefore, in such a case, you have to retain the sine terms. Okay? Conversely, you can look at an example where you want f dash 0 equal to 0. Okay? The derivative equal to 0. For example, we talked about Neumann boundary conditions, okay, where the derivative may be 0. In that case, you have to retain the cosine terms, because if you take just the sine terms, then you can never satisfy that equation. All right? So both terms are important, and depending on the situation, you may use either the sine series or the cosine series, or a combination. Okay? Now, because both terms are important, typically what people do is instead of writing the Fourier series as sines and cosines, they use this alternative form of the Fourier series using complex numbers. Okay, and this is known as the Euler representation, where you write the Fourier series as some constant times e to the power I n x. Okay, and of course e to the power I n x is cosine nx plus I sine nx. Okay, so we retain both the cosine and sine terms by doing that. And it is also easier to work with the exponential functions than with the sine and cosine functions. Okay, so this is something that Euler came up with, and when we do a finite range expansion, so this is in from minus infinity to plus infinity, but of course that's not what we are interested in. So for example, if I wanted to write my error epsilon as a function of x, so I have x going from 0 to L. I want to write my error in that computational domain as a function of x. I don't want a minus infinity to plus infinity range. I need 0 to L, okay, which is called the half range finite expansion. All right. So in that case, you modify the Fourier series, and that's what it becomes. Okay, basically the phase angle changes right there. So next thing what we will do is we will take this, our half range expansion, and use that to calculate the eigenvalues. Okay, so let's see how we can do that. So first of all, a little bit of background. Here is what, let's say, an error looks like. So what I'm plotting here is, this is of course a mock curve. I've just drawn something freehand, but your error may look like that. So suppose this is my error as a function of x at iteration k. Okay, and here is your x-axis from 0 to L for a one-dimensional problem. So you're doing iteration. At every iteration you have certain error, convergence error, which is the difference between the solution phi at that iteration minus the exact solution. Okay, that's your error, which may look like that, let's say. Okay, and we can write a Fourier series for that in that form. Okay, now when you get to the discrete representation, of course you have a set of nodes. Okay, and at each node you have a value of the error. Okay, so that's what I've drawn here. That zigzag curve is essentially piecewise lines joining the errors that you have at each point. Okay, in this case you have the same Fourier series. The only difference is you have a finite number of terms. Okay, and why is that? That's because if you have, let's say, 10 points, any wavelength in the error that I have drawn here, the continuous curve, any wavelength that is smaller than the grid spacing cannot even be resolved. Okay, so therefore you have to have a finite number of terms in the Fourier series, because the Fourier series cannot support wavelengths that are smaller than the grid size in this case. Okay, so that's why we have a finite number of terms here. So the only difference between this representation and that representation is in the total number of terms in the Fourier series that we are using. Okay. Any questions so far? Okay, so I talked about that already. So our solution is only available at grid points, and we have to use the discrete representation. Now here are some simplifications I'm making to the equation. So I'm going to kind of renumber the nodes in this case just for the sake of easy math. So instead of starting from, so first of all, instead of using the index I, I'm using j, because we are reserving I for square root of -1. Obviously we are working with complex numbers here. Okay, e to the power minus I n x. So we'll use j index for nodes, okay, instead of I. That's the first thing. Second thing is, instead of starting from j equal to 1 and going up to j equal to m, we have shifted it a little bit, and we are using j equal to 0 to j equal to m minus 1. Okay, same idea, just the index has been shifted, and that's because if you do that, then the math becomes slightly easier. Okay, no other reason. You can do it with j equal to 1 and m. You just have to transform the Fourier series, because the Fourier series starts with index 0. Okay. So if we do that, then our xj, which is the nodal location, is j times delta x. So j equal to 0 gives me 0, which is the left end, and j equal to m minus 1 gives me L. Okay, so therefore my xj over L, this actually shows up in my Fourier series, you'll see shortly, is simply j over m minus 1. Okay, the delta x cancels out. So my Fourier series, which had the xj over L right here, I've replaced that there. Okay. And we're going to again use another notation, the phase angle, which we are going to call m pi over m minus 1. Okay, so that's basically right here. So club that into a theta m so that our series becomes am exponential of ij theta m. Okay, now I just want to stop and emphasize again what these quantities are. Epsilon is the error at any nodal location j and iteration k. Okay, so what is that? If I asked you to, let's say, tabulate your value of epsilon j superscript k, all you do is you go to the kth iteration, let's say 5th iteration, you take your phi values, you subtract out the exact numerical solution, which you of course have to know. Okay, let's say you got it by direct solution or something like that. Okay, and for each nodal value you put a point, you plot your value. That's what epsilon j is, and we're saying now we can write it in terms of a Fourier series which looks like that. Okay, the I is the complex number, j is the nodal location, m is the Fourier mode, which is right here. Okay, so it's a linear combination of many different waves. That's what we're saying. Notice here that the amplitude also has a superscript k. So we are looking at what is the amplitude of that wave at the kth iteration. Suppose I have 5 waves, okay, at a given iteration. Next iteration, I now look at those same 5 waves, but I am now going to look at, has the amplitude of the wave grown or decayed? Okay, if the amplitude of one or more waves are continuing to grow, then I'm in trouble, because that one single component is going to blow up my solution. All right. If the amplitudes of all the waves are decaying, then I'm going to get a converged solution, because the error will ultimately go to 0. Okay. By doing the Fourier decomposition, we are pinpointing that. We are saying, okay, I have 5 waves, but the third wave is the culprit. That's the guy who is blowing up. Okay. So that's what we are doing. We are doing the spectral decomposition with the purpose of pinpointing which component is the culprit. All right. Any questions? So here is an example. Okay, this makes you understand the whole thing better. Suppose I have m equal to 7. So basically my number of grid points is 6. Okay, m equal to 7 means j going from 0 to m minus 1, or 7 actually. 0, 1, 2, 3, 4, 5, 6. Okay. So here is the nodal arrangement. You're going from 0 to 6. Okay, you can see those 7 nodes. Okay. On top of that, what I have plotted are, so now if you go and look at your Fourier series, there are 6 waves, because here m is going from 0 to 7. There are 7 waves. Of course, the first one is a constant, because you're going to get theta m is going to be 0. See, if you plug in m equal to 0, you get 0. E to the power 0 is 1. Okay. So the first one, of course, when you write a Fourier series, it will be a constant plus other terms. Okay, so the first term is the constant. It cannot grow or decay. All right. Then you have 6 other waves that may grow or decay. Their amplitudes may grow or decay. So here I have plotted just 4 of those 6 waves. Theta 1 through, well, I've plotted theta 1, 2, 3, and 6. Okay. So theta 1 is this big pink wave which connects the 2 ends. Okay, think of these as strings vibrating. And then theta 6 is the one that passes through, that basically has a 0 value at all the nodal points. Okay? And then you have these intermediate ones, which are also playing a role. Now, if you think of this, okay, these are strings vibrating. The question really we are asking is, once you set it in motion, in vibration, which of them will just, just oscillate and then boom, blow up, okay? Versus which of them will just, slowly collapse down to the straight line, down below. That's basically what we're saying, okay? So, Dirichlet boundary conditions, the error by definition on the two walls are 0. So basically we are looking at only the sine waves here. We are not looking at the cosine waves. Even though we will be working with complex exponentials, the only components we are interested in here are the sine components. Okay, the cosine components doesn't matter. So that's why I've drawn the sine waves, because otherwise you cannot enforce these two boundary conditions, that the error is 0 at the two boundaries. Okay, so that's that. So let's see how now we can apply that to finding our eigenvalues. Okay, so we start with a very simple example. Second order ordinary differential equation. Okay, here's our discrete form, finite difference. And I'm just rewriting it in a different way. So phi j minus half phi j plus 1 minus half phi j minus 1 equal to 0. If I write it in Gauss-Seidel iteration form from left to right sweep, okay, then this is what the iteration equation looks like. So the j and the j minus 1 have index k plus 1, and the j plus 1 has an index k, because the one to the right is always treated explicitly. Okay? Everybody understand that? All right. Exact solution will also satisfy the same equation. So we can write that equation. We subtract one from the other, we get our equation for the error. Okay, so epsilon j k plus 1 minus half epsilon j k plus 1 j minus 1 at k plus 1, and then on the right hand side we have the j plus 1 with superscript k. Okay, now each of the error terms can be represented as a Fourier series, and that's what we are going to do now. Now what I have done here is, now this is not a necessity, this is again to simplify the math. Okay, instead of starting with j equal to 0 here and then going up to m minus 1, I've started with j equal to 0 right here for the central node j. Okay, and then this is j plus 1 and this is j minus 1. So I've used 0 for this guy, so that becomes a plus 1 and that becomes a minus 1. Okay, but this is not a necessity. I can show you I mean, you can do the derivation without doing that. It just some certain extra terms show up which cancel out. Okay. So now we are going to take this and plug it into our iteration equation. Okay. So we'll take the Fourier series, plug it into that equation. And when we do that, this is what we are going to get. So notice that this one has j k plus 1. So I'm going to use, instead of j, I'm going to use j equal to 0. So that gives me e to the power 0. And then the amplitude will have a superscript k plus 1, because this is epsilon at k plus 1. Okay. Similarly here I have a minus half. Again, the amplitude has k plus 1. And then the j minus 1 is basically replaced by j equal to minus 1, and that gives me e to the power minus I theta. Okay, and then on the other side I have amplitude k, because this is epsilon at k, and then the j plus 1 gives me e to the power plus I theta. Okay, now if I didn't do that, if I didn't shift the index, okay, then here I'm going to get e to the power I j theta m. Here I'm going to get e to the power I j plus or j minus 1 theta m, and e to the power I j plus 1 theta m. And what you will find is that e to the power j theta m will just cancel out. Okay, and you'll be left with this equation. All right. So shifting the index just simplifies the math a little bit. Any questions on that? These are important steps that we'll be doing for all iterative methods. Okay, so if I simplify further, e to the power 0 is 1, so that goes away, and then I'm left with those two other terms. All right? Now, here is where the independence of the Fourier series comes out. Okay, so we're saying, okay, this is a relationship which has summations everywhere, but we know that this relationship needs to be satisfied by every Fourier component, because we cannot linearly combine two Fourier components to give us a third one. Okay, so that's the argument. The linear independence is what we are using to now say that, okay, we drop the summation and we simply have that equation. Every Fourier mode must obey that equation. Okay, Fourier mode being m. Okay, every m must satisfy that equation. All right, so this is for all m going from 0 to m minus 1. Okay, now this sign I'm using here, this means for all. Some of you may see it in the notes and it might be confusing, but that's what mathematicians use for all. Okay, so we rearrange that now, and we rewrite this as the amplitude ratio. This is the ratio of the amplitude between the k plus 1th iteration and kth iteration. Okay. Now it turns out, this is where I'm not offering any proof, is that that amplitude is nothing but the eigenvalue of the B matrix. Okay. It is the mth eigenvalue of the B matrix. Okay, this guy here, this amplitude ratio. Okay, so obviously, and intuitively we know that if that amplitude ratio is greater than 1, bad news. If that amplitude ratio is less than 1, good news. Okay, so it goes hand in hand with what we said about the eigenvalue. If the eigenvalue is greater than 1, then not good. All right, doesn't meet our stability criterion. So basically we are saying for all values of m, this amplitude ratio must be less than 1. Then the error will decay. Otherwise, the error will grow and the solution will blow up. Yeah.
So the first condition that we have for all m from 0 to n minus 1.
Yeah.
This is the condition that means for all those strings to make all of them
collapse to 0. Yes.
That's why we just omitted the summation.
That's right. Okay. Now, what we are saying here, though, is that this is for all values of m, but really, now that we get to this point here, that we know this is the eigenvalue, all we can say is, okay, which is the worst wave? Which one has the biggest probability of not doing that? Can we identify that and just focus on that one? Okay. So we are going to, next step, what we are going to do is we are going to try to identify which of these ratios is the worst case scenario, okay, of all the different values of m. Okay, now let's proceed with the math and then we'll answer that question. So this is our eigenvalue, okay, that I have from the previous page. All I've done here is just I've multiplied and divided by 2, so that instead of a half I have a nice expression. Okay, so to calculate the eigenvalue, what you have to do is, because this could be a complex number, you need to take the complex conjugate. Okay, so you take the lambda and its complex conjugate and then multiply the 2 and take its square root. This is basically finding the magnitude of a complex number. All right, so I have e to the power plus I theta m, here I have a minus I theta m, and then here also the sign changed. Okay, and I'll show you how to do it in general terms later on. Okay, but this is your lambda and this is your lambda conjugate. Okay, so we multiply the 2 and then take the square root. So let's keep simplifying this. So on the top, of course, the 2e to the power I theta m and minus I theta m gives you a 1, and then in the bottom you just multiply that out. Okay, you get 4 plus exponential of 0 minus 2 times e to the power I theta m plus e to the power minus I theta m, which you expand as cosine theta m plus I sine theta m, cosine theta m minus I sine theta m. These two guys cancel out, okay, and you're left with that. Okay, so that's your eigenvalue. Again, this has an index m, this has an index m right there. So there are m eigenvalues going from, in this case, 0 all the way to 6. Okay. Now let's look at this function. So in this case, capital M is equal to 7, and therefore your theta m is m pi over m minus 1, which is m pi over 6. All right. Now, if you look at the cosine theta m, okay, so the range of theta, if you look at this expression here, is between 0, so m is equal to 0 gives me a 0, and then when I plug in m equal to 6, it gives me pi. Okay, so that's the range I'm looking at, 0 to pi. So in the range 0 to pi, cosine theta m is decreasing, okay, with increasing theta m, and so therefore this guy is actually increasing, decreasing with increasing value of m. Okay. So in other words, large values of m are not of interest because it's going to give me the small eigenvalues. Okay. It's the large values of, or the small values of m that we are interested in. Okay. Now what is the smallest value of m? Obviously 0. But 0 basically gives us the constant term of the Fourier series. I talked about this before, because you have e to the power I theta m's. When theta m is 0, you basically get amplitude times nothing. Okay, it's a constant. It's not a wave. It's like, you know, when we write polynomials, we start with a constant, then we have x, x squared, and so on. Same thing with the Fourier series. We start with the constant. Okay, so the first wave corresponding to m equal to 0 is a constant. It cannot grow or decay at all. Okay, so really the one that is of interest, so this is what I've put this expression here just for you to see. So if theta m is equal to 0, then nothing really happens. Okay, just get the constant. So therefore the one that's of interest is m equal to 1. Okay, m equal to 1 means we are looking at the theta 1 component, pi over 6. Okay, so when I calculate the eigenvalue for theta 1, I get 0.81. Okay, that means that in this particular case, for this problem, the Gauss-Seidel scheme is going to converge, because the eigenvalue, the largest eigenvalue, is less than 1, 0.81. Okay. Now let's look at it pictorially for a moment. What is this theta 1 or pi over 6 wave? It's this guy here, the pink one. Okay. Now if you start thinking about this a little bit, it kind of makes sense, because again, if you start thinking about strings vibrating, that guy, the pink one, is the freest string, because it is not anchored anywhere except the boundaries. Okay, it has maximum flexibility to do whatever it wants. Okay, all the other strings are anchored at some point or the other inside the domain, because you're forcing it to go to 0. Okay, so these are the anchoring points, as you can see. Okay, but that wave, this guy here, is free to do whatever it wants. Okay, so this is the largest wavelength we are talking about. So one of the things, one of the lessons that we want to learn out of this is that convergence problem is always created by the large wavelength components of the error. Okay, the small wavelength components or the high frequency components don't pose any problems. Okay, it is always that large wavelength component that creates problems for us, and therefore somehow we have to damp it out efficiently. Yeah.
I just have a question.
Yeah.
So that equation is dependent on your differences.
Yes, this is what we are saying here is for the Gauss-Seidel scheme. Okay. Now it turns out that that's a very good question. It turns out, even though I'm explaining this using an example, it turns out that the fact that the largest wave number, or m equal to 1, is the culprit is true for any iterative scheme. Okay? That always produces the largest eigenvalue. Okay? So, but your point is very well taken that this example is for this particular Gauss-Seidel scheme, second order ordinary differential equation. Okay? But it kind of helps us to understand what's happening. Any other questions? So remember this, that m equal to 1 is always our culprit, and that corresponds to the largest wavelength. Okay? All right. What happens if we now, let's say, increase the number of mesh points? Go from 7 to 14, double. Okay? Then our theta 1 becomes, again, m, remember that's theta m is m pi over m minus 1. So this is now 14, so that's becomes 13. And then we are always looking at the small m equal to 1 component. Okay? So that's what that gives us, and then when you do the calculation, we get 0.95. So what has happened is m equal to 7, we got 0.81, m equal to 14, so same scheme, Gauss-Seidel, one-dimensional problem, our eigenvalue has gone up. Okay? It's still stable, so both will work, all right? But we'll find out soon what that means. So finer mesh, the iteration scheme is still stable. However, note that the spectral radius has increased, all right? What about the rate of convergence in the two cases? Now, the rate of convergence depends on this ratio. We talked about this, the condition number of the B matrix, okay? We've already calculated that guy, the numerator. Let's now calculate the denominator. Okay? Denominator will correspond to the maximum value of m. Okay? So lambda max corresponds to the smallest value of m. If you go back to that expression 1 minus 5 or 1 divided by 5 minus 4 cosine theta, okay, the largest value of m will give you the smallest value of lambda. Okay? So we are looking at the largest value of m, which is m minus 1. So therefore theta m is nothing but m minus 1 pi over m minus 1, which is pi. Okay? The interesting finding here is that it is independent of mesh size or anything like that. As long as we retain the same iterative scheme, okay, Gauss-Seidel, this formula will be valid, and that formula, all we are going to do is we are going to use pi for theta m. Okay? So what I'm trying to say here is that the fact that I changed, let's say, from m equal to 7 to m equal to 14 didn't change the lambda min at all. It still corresponds to theta m equal to pi. See, in this formula, there is no other grid spacing anywhere else. Okay? All I do here is plug in pi. That's it. So that gives me then 0.33 for lambda min. Okay? And so you see the minimum eigenvalue is unaltered by the mesh size, which in this case corresponds to capital M, the number of node points. Okay? Only the maximum value is altered by the mesh size. So what does that mean? That means that the larger the spectral radius of convergence, the slower the convergence for a given iterative scheme. So if I'm looking at solving the same problem using Gauss-Seidel, let's say, if one of them gives me a larger spectral radius, then that means that would also be slow convergence. Okay? This is something you will find time and again in homework 3, homework 4, all the iterative solvers that you work with. Okay? You will find that when you refine the mesh, all of a sudden number of iterations has increased dramatically. And that's because the condition number of the matrix changes. It's no longer the same. Okay. Any questions? So these are very, very important points to note here. Smallest value unaltered by mesh size, largest eigenvalue increases as the mesh size is refined. And so as a result, the condition number also increases and gives you poor convergence for a given iterative method. Once we get outside that realm of the same iterative method, then the lambda min, if you compare Gauss-Seidel to ADI, the lambda min also will change, okay, from method to method. So you can't really just take the lambda max and compare. Okay, you actually have to calculate the condition number and compare. So what are the implications of slow convergence? Okay, and sometimes, you know, it's easy enough to understand, but I find it difficult to convey to students what it really means. Okay, so think of it this way: if the number of nodes is doubled, it implies that roughly double the workload per iteration will be performed. Why? Because suppose you double the number of nodes, basically your loop has become twice in size, right? The same 5 multiplications you're doing for twice the number of nodes. So that's twice increase in workload. Okay? Simply double the loop size. That's all. Okay? But now we're saying, okay, we are doing it for twice as number of nodes, but instead of taking 100 iterations, it's now taking 400 iterations to converge. So essentially, your total workload has gone up by 2 times however much factor the number of iterations has increased by. Okay? And that's nonlinear scaling, which is really bad news, which means the larger the problem you solve, the worse off you are. At some point, you will get to a stage where you will say the method is unusable. It's not scaling at all. Okay, when I use it for 1,000 nodes, it works fine. By the time I'm at 10,000, it's super slow. By the time I'm at 100,000, then I'm just sitting there forever. Okay, it's not working. So this is the problem. And in homework 3, for example, you know, and I encourage you to do this, I've asked you to calculate for 41 by 41 and 81 by 81. Okay, note down the number of iterations in each case, of course, okay, and look at the scaling of that number. What did it scale by? Typically, you will find it's somewhere in the range of 4. So what does that mean? That means to solve the problem on this mesh, it takes 16 times more, or not 16, 4 times 4, yeah, 16 times more computational time. So if you're solving this in 1 hour, this will take 16 hours, not 4 hours. Okay, ideally we would like 4 hours. That's still, of course, better than Gaussian elimination, if you think about it, because that's cubic scaling. Okay, this one is at least, we're talking quadratic scaling. Okay. Any questions? Yeah. Oh, no. We're looking total number of equations. Okay. From here to here, this is just increase in a factor of 4 in the number of equations. Yeah.
Question about this Savoy analysis. I mean, the most significant equation that is governing in the Savoy analysis is the relation between lambda m and theta m. But in this spatial scheme that we look at, we see that it's a kind of uniform function that if we increase theta m, the lambda m will be decreased definitely. So it has a uniform behavior. So I want to know that is any rule governing on this equation that for all other schemes we will have such a kind of function that by increasing or decreasing the theta m, we can find a critical value for lambda m, so that we can say, okay, in this specific point, it's the minimum or maximum, or maybe it happens that, for example, we don't have any maximum or minimum for that.
Yeah, that's a very good question. So what people have found is that the largest eigenvalue is always given by m equal to 1. Now, in between, it may not be monotonic behavior. Okay. In other words, sometimes you will find that m equal to 6 behaves better than m equal to 12. Okay. But the two endpoints they've always found gives you the largest and the smallest eigenvalue. Okay. Now, there is, I can refer you to a book where you will find detailed derivation of that. Okay. But that's what is known. There is, beyond that I can't tell you anything else.
So the critical points are always the first one and the last one.
The last one. Yes. Yes. Okay. Any other questions? All right. So let's move on. So here is this is the last slide. This is sort of like a miscellaneous slide I have for general procedure for complex conjugate calculations. Now, many of you have fancy calculators now. In my time, I never had calculators that could process complex numbers, but now you do. So, if you have a calculator like that, feel free to use it and crunch out your numbers. Okay, you don't have to go through this. But for those of you who don't, or who may want to write a program, let's say a little MATLAB script to calculate the eigenvalues, this is what you basically do. You always decompose the number, the complex number, into this form first. A plus bi divided by c plus di. Okay? So I'll show you an example in a minute. When you do that, then the complex conjugate can be calculated in this way. So what you do is so first of all, to calculate the magnitude, what you do is you multiply numerator and denominator by c minus id. So basically you try to get rid of the I in the denominator. Okay, and so you multiply it by c minus id, so the denominator becomes c squared plus d squared, and then the numerator becomes something else. Okay, and then basically you have something of the form a plus ib, and you can easily calculate the complex conjugate, okay, because the conjugate is a minus ib. All right, and then you take the magnitude. So that's what you get. That's a formula that you can just use. So suppose I go back to this example I have here. Okay, I can break that into cosine theta plus I sine theta, and break this into 2 minus cosine theta plus I sine theta. So you can clearly see this here becomes my A, this is my B, this is my C, and then this is my D. Okay, and I just take that, plug it into this formula, that gives me my eigenvalue. Okay, so this is just a general procedure for calculating in case, because a lot of times you'll find, I mean, this is a simple example, but later on you'll find that when we work with these expressions, sometimes you'll get really big, humongous expression with e to the power I theta, 2I theta, minus I theta, minus 2I theta, and so forth. Okay, and then by the time we get to 2D, you will have I theta x, I theta y, and so on. Okay, so this is just a general procedure. Any questions? So just to summarize, what we learned today is that the most important takeaway is that, number one, the stability criterion is that the maximum eigenvalue, which is called the spectral radius of convergence, must be less than 1. Okay. To calculate that, we do a Fourier decomposition, and what we find from the Fourier decomposition is that the largest wavelength is always the culprit. That corresponds to that m equal to 1 in the Fourier series, and therefore we always focus on that. Okay, and we find the eigenvalue corresponding to that. And if that's less than 1, then that's good news. Otherwise, we are in trouble. So I'll show you a lot of examples down the road in the next class and the one after.